Okay, this is where we were. Well, we actually already covered this, but find, right? Find, it's a linear search, but it returns a -1 if we don't find it. And we talked last time, I changed that -1 to a not found. I made it a constant, not found, which is kind of nice, right? Otherwise, it's not a magic number. We all know that it should be, exactly. That's how you know he's late. So there we go, that's the find. It's simply a linear search. And you'll note here, S equals student. Well, it's checking for student equality. How does it know if two students are considered equal? Well, based on the student classes equals method, which is written right up here, right? We've defined it here. And it's equal if their student numbers are the same. Okay, cool. This is like functionally equivalent to, where's the find? This is like functionally, it's like equivalent to like S dot student number equals right? This would be equivalent because students equals is checking that. Functionally equivalent is what I mean. Was that clear? It better be. If not, we're in trouble. Okay, so that's the find. And then with find, we were able to write these two other methods. And remember, the idea with the find is, yeah, it's important for the inner workings of the class, because like look at contains. Contains just calls find, and it checks did it get not found. And remove calls find as well. It just returns the student at, there. Great. Or removes, yeah. So it's important for the inner workings of the class, but I have no intention of calling it from outside the class. So that's why that underscore is there. It's signal to the other programmers, including yourself, that this method is, yeah, it's used inside the class. It's important for its inner mechanics, but outside the class, not overly important. And yeah, remove. Okay, contains, yeah, there we go. Remove. And here we're making use of contains and find. We could rewrite this a bajillion different ways, right? I just did it this way. If not self-contains that student, it's not there. We can't return anything. Oh, and this is my modified version from what we originally had. Let me go back real quick to the here. Yeah. Here, if self not contains, I raise a value error. That's what I did in the example here, which is one way to go about doing it. If I say, okay, hey, remove the student from the class. That student's not in the class. What's going on here, right? So like maybe something peculiar is going on. So we raise the exception for the programmer to deal with it accordingly. Or we could do an alternative version, which is what I have here. I just changed it here for fun, where now instead of raising the exception, this will return a Boolean that will signify its success or failure. But it won't crash, like it won't raise an exception that needs to be caught. So if not there, return false. I just didn't do anything. Otherwise, remove it, return true. Remove it from where? We'll go to the students list and pop, which means remove something. Which one? Well, the index of that student that find returns. Cool? Cool. Okay, and then finally, repr. Now, here's kind of where, remember with the student class, how I did its repr differently, right? Where I did it, instead of like student parenthesis, attribute, 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 I'm doing it this way. I want last name, comma, first name, tab, student number. Why? Because when I have a whole course of students, I want to see the students in a way where it's like a list of students with their names and student numbers, right? Not a student parenthesis, first name, comma, like that's just too much. This is an example of like before when I said that general pattern for a repr, you only use that pattern when you don't have any idea in mind. But when you have an idea for what you want it to look like, you implement that instead. And so that's what I want it to look like. So because I want my course to basically be a list of all the students, that's what I'm going to do. So I start with an empty string. Now remember, strings are immutable, but you can like create new strings by appending strings together, right? So I start with an empty string, and then I say for each student in students, so each time through the list of underscore students, this is a student object. And what do? Is I say, well, append to that empty string. I'm doing F strings. And if you do an F string like this with the specific student, that'll call the repr automatically. So this calls the student's repr. New line. And then for the next student, student, new line, student, new line, student, new line, and so on. And then once we're done, we return that whole string, which contains every student line after line. Yeah?
Did you say it was the F string that caused the student's repr to be called?
Yes.
Okay.
Now, here, let me show you here. Because like when you do this, F, and then you put like these braces, the squiggly brackets, that means, oh, give me the string representation of this value, which will then automatically call the repr. Okay. If you were to do like this, it's the same thing, right? Okay. Yeah, it just this like does it automatically. But if we include this, now that's pretty cool. It's going to make more sense though if we have an example. So I'm going to take this. No problem. If I print it out, now we see. Now, because we're using tabs, you know how sometimes if you're tabbing things in the number of spaces, it'll get, so it's not going to format perfectly because Niles McDonald's name is just too long, I guess. But the first student, it's Bob Smith, Jane Doe, Niles McDonald, Jane, there's another Jane Doe, I guess, right? Do you see how, think of how that repr works. I start with an empty string, and then I append to it the string version of the first student. Well, that's should be Smith, Bob, blah, 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 blah. Then the next one, then the next one, then the next one. So do you see how calling the repr on the course goes and calls the repr on the individual contents of the thing within the course, the students? That's exactly how it works in the list as well. Think of a list. You ever print out a list? Well, the list formats with like bracket, value, comma, value, comma, value, right? But each value in the list's repr gets called. Like, let me show you. Let me give you an example here. Let's say, ignore the course for a second. Equals that. No, here, I'll just do. I'll just add a bunch of Bobs. If I go down here and then I print out, see how, well, the list, it's doing that list thing where it's bracket, value, comma, value, so that's the bracket. Value, comma, value, comma, value, comma. Now there's some in comma in these strings because that's the string representation of the, like, this could be confusing. You'd look at this and be like, well, what's the length of the string, or of this list? You'd be like, well, 1, 2, 3, 4. But that's actually not right, right? Because this comma is part of the string representation of Bob Smith. You see? Where this comma separates it from the, or no, this comma separates them. You see? Here, let me just get rid of that. There. This might make it a little nicer. There. There. Do you see? So this is the string representation of the first thing in the list. Well, it's the string representation of that. So this is the, like the list's repr will go and call the individual reprs for each of its contents. Pretty cool, eh? That's what we're doing right here. I'm going to add that comma back in. I like it. Okay. Any questions, thoughts, concerns, comments, or anything? You will have noticed, and I brought this up in office hours to someone today, you will notice that, like, I feel Like, just to personally, everyone's different. If you disagree with me, great. It doesn't matter. It's okay. I feel like the learning curve of this class is like this, right? Like, yeah. This is garbage, this one. Right? This is time as we learn stuff, right? And this is difficulty. Angry. So it starts fairly easy. Print hello world, right? And remember that the difficulty doesn't come from learning how to print, what a value is, what a function is. It's putting all of it together. That's the difficulty. I know I'm a broken record. It's not about knowing how to use a hammer or a saw or a screwdriver. It's about knowing how to build a house, right? That's what we're learning. I'm not teaching you how to pick up a hammer. That would be, picking up a hammer is the analog of like, this is a function. Picking up a screwdriver is, this is a loop. Building a house is, make tic-tac-toe. Use all of those tools to do something, put it together. So that's like really where the difficulty comes. Every time you add a new tool, you can do more interesting things. So the difficulty kind of goes like this, right? And then we hit lit. Let's say this is like lists. And lists are kind of like our linear collections or something, right? I'm not talking about the classes yet or our data structures. I'm talking about lists. But then personally, I feel like once we hit classes, it kind of tapers off a bit. You might not agree with me, but this is what I think. And I think it's because, well, with classes, it's applying what you already know, just, in classes to like build stuff in a way, right? It's still just building stuff. So I'm not giving you like a huge new tool, right? That's not to say like, look, by the time we get to data structures, yeah, there's definitely still an increase there, right? It's still growing, okay? But that's kind of how I feel how things are. So if you're at a stage where you're like, am I missing something? Are classes like too easy? What's going on? It's not that they're easy. It's that you've already kind of like made it over the biggest hurdle at this stage, okay? That's kind of the point I'm making. It's not to say that this is trivial. No, 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 absolutely not. If you're working through assignment 4, beating your head against that keyboard, you know it's anything but trivial. But you're not like, this is what raise your hand if you somewhat agree with what I'm saying. Maybe not precisely, but to some degree, you kind of know you get what I mean. Okay, that's, okay, cool, cool. Again, that doesn't mean, like, look, this part right here, if you're like, volume of stuff I need to, the scale, the exam cares about this stuff, okay? I'm not going to ask you print hello world on the exam, I'm sorry, all right? I know, if you were counting on that, I'm sorry. What about a bonus question? 25% of the test. Do you think that's a good idea? Yeah? Why not? Because somebody would want to hire you eventually, and then you'd be like, what did you learn? What was on your exam in your first programming course? They say hello world. You're going to be like, what the,
Okay,
what?
hello world, guys.
You'll be like, well, at your job, they're like, we need someone to do hello world. I know just the guy.
Yeah, exactly.
I gotcha. Okay, all right. All right, so do we have any questions? All right, so now that I just finished saying that, how we've kind of tapered off a bit, I'm about to do a little bit of this. Okay, so all right, just bear with me though. Okay, it's probably not as bad as I made it look, but that's about to happen. Okay? First, we're going to start talking about, well, you'll see. We're moving away from classes explicitly at this stage. And we're about to start talking about, first we're going to start talking about searching, okay? And you already know what a linear search is. So I'm not teaching you a new algorithm, but I want to take a step back and think about searching. And then the next topic is sorting. And that's really, well, that's that. All right, so before we continue, let's take a moment and really think. I think you'd have a hard time finding a course that you could take as a first-year course at a university where you're going to learn more concrete technical skills. You're probably not going to find a course. There's not going to be very many courses that can beat this one. And, well, first of all, writing software, of course, is a big thing. But, like, you know what the programming environments are. You know how to get, like, you know how to do I/O. You know what values are, types. You know about variables. You know about literals. You know about functions. You can write them. You can use them. You know about the basic propositional logic, like your if, your true, false, and whatnot, how you can do conditionals. You know about loops, like iteration, both for and while loops. You know about what objects are, both how to build them and how to use them, like you know what methods and attributes are. You know about linear data structures like lists, which are a big one. If they're like, that is like, this is probably the most popular big data structure tool that will, like, you will use this probably like 99% of the time when it comes to data structures. I pulled that number out of my ass, but a lot. You also have an idea about like how references work versus like the primitive types, how like what's stored in that variable really. You know how to do like input-output from files. We know how to write our own class. You talked about that. You know a little bit about exceptions as well. You know how to write your own code one step at a time. You've developed debugging strategies for writing software. That's like, you know, kind of like bigger sum of their parts. You can look at existing, should at this stage be able to look at Python code that is perhaps more advanced than what we've learned, but still be able to figure out what it does. So like if I were to show you some code where it contained, this not on the exam, but like if I gave you a chunk of code that includes Python stuff that you've never seen before, but given your current level of experience and its context, you should be able to figure out what's going on to a degree. You know about how important testing is, writing and running your own unit tests as well. And not only ensuring correctness, but about thinking about your code. I've made sure you've spent time thinking about like the syntax in terms of how it communicates the semantics of what it means. Remember, syntax is like what you've written. The semantics is like what it's doing, what it means, okay? I made this analogy in office hours today. Like, I know when you submit your assignment, you submit the code, right? In the same way that like, raise your hand if you've like written an essay for school before, right? Like, in the same way that like your essay is about the words that you wrote on the paper. That's not what the essay is. The essay is, what are you saying? What are your arguments, right? The words that you wrote are just incidental. Like they're a means to communicate the ideas, right? It's kind of like the same idea there. So I'm hoping you get an appreciation about like, okay, what is the code doing and what's the implementation, the algorithm versus the implementation, right? Those details are important. The last few topics have been big on objects and data structures, and that's important, right? Because we need to equip ourselves with all the major tools that we need going forward. But I want to take a step back and shift to algorithms a bit. Everything we've written before has been an algorithm, but a big part of computer science is the algorithms themselves, what they mean, how they work, are they good, are they bad, a bunch of different things like that. So, linear search. We already know what a linear search is. If this is surprising to you, you're in trouble. What is a linear search? Given some collection of things, haystack, and a thing I want to find, needle, for each element in haystack, if element's what I'm looking for, I found it. If it's not, keep going. And if this loop ever finishes, it can only ever finish if this line never ran. Because if it returns, it stops. So if we never found what we're looking for, and we're out of things to look at, it's not there. There's your linear search. This should not be mind-blowing to anybody. Having a correct algorithm is obviously important. But having a good algorithm is important. But what does it mean for an algorithm to be good? Now, we have talked about this before, but I'm going to give you a chance to talk amongst yourselves. Like on average, how many times does that loop need to run on a linear search to find the needle? Assuming it exists, let's say. If the element you're looking for is not in the list, how many times will the loop run? What would the situation cause to need the loop to run like the minimal number of times? Pardon me. Is this the best solution you can think? Is there a better way to search for things? Do you know of a better way to search for things? How much space does this algorithm like require to run? Right? Like take a moment, talk amongst yourself. I'm not asking you, I want you to talk and discuss with each other and think about these things. Because these are all the considerations you need to really think about in order to answer the question, is this a good algorithm? You have a clarification question?
Yeah, I was going to say, can we please see the code?
Yeah, you bet. Here, let's, shoot, that won't work. Cool, so yeah, there you go. It's too quiet in here to hear you talking to each other. You're not talking, get talking. If you're far away, move. Yeah, you can assume it's like a list of integers. Yeah.
That's smart. That cuts down the number of words you'd have to look through. That's smart. But that yeah. Yeah, because that would be, it would stop at like the first one letter. Like say there's like start and there's like sustain. If you want to get to sustain, but start is above sustain, it'll go to start and be like, oh, okay.
Does anyone in here have a textbook on them? Like a good thick one?
Wait, like a writing one?
No, like a, not a writing one, just like a textbook.
I have one, but it ain't thick.
I need a thick one. Just for demonstration purposes. Well, that can't be thick. That'll do the trick. That's perfect. No, they're thinking about it. I can hear it. Yeah. Does anyone have any follow-up questions about this one yet at this stage, or comments or anything? We don't have to explicitly answer these things, but I mean, okay. Actually, let's do it real quick. On average, how many things does it need to look at, assuming it's there? Given a list of length n, on average, n over 2, right? Because for every time it's at index 0, it's at index n minus 1, right? So like on average, somewhere in the middle. Okay. If the element's not looking, if the element you're looking for isn't there, how many things do you have to look at? All of them. What would the situation be such that the loop needs to run as little amount of times as possible?
The thing we're looking for is
Yeah, like, is this the thing I'm looking for? Yes! Great. Right? Of course. How much space does this algorithm take up? It's kind of a weird question to ask, but like, well, n. The n numbers I need to look at, they got to be stored somewhere, right? So these are all considerations we think about when thinking about like algorithm goodness. But the big one is, okay, that's great and all, but is there a better algorithm? I need a volunteer. I'm going to, no, because you're going to do something annoying if I pick you. You're going to be my volunteer. So here's what you're going to do, and you're going to have to help them a little bit, but don't worry, you don't have to do much. You're going to pick a number between 0 and 1,023. Okay? Don't say it out loud. Okay? Say it to him, though. Okay? Do you have it? Perfect. So, I'm going to guess your number. All right? Everyone listen to what I'm going to do. Is it 0? Is it 1? Is it 2? Is it 3? Is it 4? Is it 5? How many numbers do I have to pick? How many numbers do I have to say to guarantee I pick his number? 1,024, I guess, because it's 0 to 123, yeah, or 1023. So I would have to pick, if I do it that way, it would take 1,024 guesses, right? What if I told you I can guarantee you I could find that number in 10 or less? Do you believe me? I'm used with magnets, yeah. But there's a bit of a catch, okay? There's a catch. You got to give me one thing here, okay? And by the way, I'm not about to blow your minds. I'm about to show you something you all already know. Pardon? Are we betting? What do you mean? That you already know this? Are we gambling? No? What? Here, first, I need another volunteer. All right. No, I want you, because you, yeah, it's like you don't trust me. Come up here real quick. Here, hold on. I want to see. Turn to page 250. Everyone watch him. Turn to page 250. It didn't take him 250 page flips, did it? Turn to page 320. Turn to page 100. Well, that's cheating. Okay, you go sit back down. Do you see what he was doing? Here's the catch, okay? I'm going to pick a number, but you got to give me something. You have to say higher or lower, okay? So, is it 512? Lower. I'm just doing this to not embarrass myself with not being able to do arithmetic. Well, yeah, I'm picking two. He thinks I should pick 256. Is it 256? Is it 128? Is it 64? Oh, oops, pardon me. There we go. Is it 96? Is it 80? 72? 68? 66? 67? 67. It's funny, that number actually is like one of the ones that would take the most number of guesses. But I was able to get it in 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I got it in 10 guesses. How many guesses would it have taken if I... yeah, 68, right? Because of 0, yeah. Exactly. So how was I able to do it in 10 guesses? Well, I had to cheat a little bit. I had to say higher and lower. Now, long story short, it's the same algorithm as this, right? If I say turn to page 300, right? I'm going to go like, I don't know, like this. I'm looking at page 249. So I'm going to go like this. Okay, well, clearly it's... Which side? This is page 249. This is page 248. I want to find the page 300. There are 248 pages this way and some number of pages this way. I don't know, like another 250, let's say. And I'm looking for page 300. Should I look over here? I've eliminated roughly half of the pages from my search. I know if I'm looking for 300, it must be over here. The data is ordered, it's sorted. Okay, the numbers in this book are sorted, right? So I'm going to go like this, and then I'll say like, okay, no, I turn to page, here. I'm now looking at page 426. I'm looking for page 300. This is page 249. This is page 426, and this is page 427. I'm looking for 300. Where should I look? In this part, right? Because if the page exists, which I assume it does, it should be in here. I've eliminated the another remaining half. So I'm going to go like, okay, somewhere like, I don't know, between here and here. 296. Well, now I'm getting real close, right? But the point is, I keep going. This is called like an interpolation search, but in general, the perfect case of that would be what we call a binary search, where you perfectly eliminate half of the things every time. Thanks for the book. Where you eliminate half of the things every time you make a guess. So the first time I eliminated 512, then 256, and then 128, and so on and so on and so on. Where if I do a linear search, think about it like this. If I'm looking for the number, some arbitrary number in 10,023 cases, 0 to 1023. 0. Is it 0? No. How many pages did I eliminate? 1. The other way, I eliminate half. Yeah?
It's actually the best way to play Guess Who.
Yeah, of course it would be. Yeah, it's the optimal. Yeah, absolutely. But you have to have some discrimination where you can eliminate the maximum number of people every time. But you got to be careful, because if you pick something where, like, if this is right, I'll eliminate everybody except this one person. But if I'm wrong, well, it doesn't help me very much. So you have to pick the right one. So you want it to be about like 50% of whatever's left. That's what you want to do in terms of Guess Who, if that's what you're playing. Yeah?
So would it like genuinely be have a good difference for using that instead of a linear search, like computationally? Would it actually help?
So the difference in this example is worst case scenario for a linear search is 1,024 guesses. The worst case scenario for the binary search was 10. So it seems as if it's better, but you know, in computer science, we always think of things at scale. You want to hear something crazy? Think about the linear search. If I double n, how many more questions do I have to ask in the worst case scenario?
2049.
So twice as many. If I double n for a linear search. But with the binary search, every guess, I eliminate half the things. If I double the size of n, how many more guesses do I have to make? 1. If I had 2,048 options, it would require 11 guesses only. So as n scales, you absolutely want that binary search. However, there's the big catch. What's the catch? The data's got to be sorted. Imagine that book had all of those pages on it, but they weren't in any order. Think of how much of a pain in the ass it would be to find any page. 17, 412, 205, right? Like it wouldn't work. You couldn't figure it out. So the catch is the data needs to be sorted. And it turns out sorting data, well, how many times do you get a collection of things that are sorted, right? You'll notice that like in the, if you ever come to my office hours to look at your tests, right? I'm like, what's your last name? Oh, yeah. And I can find your exam like that, right? It's because I've sorted things reasonably alphabetically. So it's easier for me to do it. But I had to sort it in the first place, which is kind of a pain in the ass. It's not too bad of a class size this big, but if you've got like 100 students, it's a pain in the ass. Because it turns out sorting is kind of hard. Okay, this is what we were talking about. Great. Okay, binary search. Yeah. Okay, yeah, we just talked about it. All right, so yeah, a little bit in complexity analysis. The magic with binary search is that with every guess, I eliminated half of the things. My first guess was 512. If you said lower, I know that it must be between 0 and 511. If you said higher, I know it must be between 513 and 1023. To generalize the idea, if I had n numbers, the guess, like I guessed the number n over 2. Then I know it would either be between 0 and n over 2 minus 1, or n over 2 plus 1 and n minus 1, right? It's in the remaining part. You already all know this algorithm. You do this algorithm. If you've ever had to turn to a page in a book, you're doing it. Perhaps not to exactly 50% because that's crazy, but you know this algorithm. This isn't anything new. How many of you have ever sorted anything before? No, never, right? Of course you have. Have you ever thought about, how did I do that? How did I sort? What were the steps I followed to sort this thing? You might say, like, I don't know, I just sorted it. Yeah, but you did follow an algorithm. But what was it? So yeah, if you follow this pattern with 1024, my guesses would eliminate this number of things every time. 5, 12, 256, 128, 64, 32, 16, 8, 4, 2, 9. Or sorry, 2, 1. Right? When I get down to here, after the 9th guess, it's a one of two numbers. Point is, this is fantastic. But with a linear search, yeah, not so bad. So it turns out, oh, this needs to be a lowercase. That's a typo. I need to fix that. This follows, where the linear search follows like in n, as you double the size, you double the amount of work. This follows, if you double the size, it grows like log base 2 of n. And whenever you see, I know people who are like, I don't like math. You see log and it spooks you. Don't be spooked. Log is, do you know what, I can guarantee you if log spooks you, you had bad math teachers. And if you think you had good math teachers and log still spooks you, you probably had bad math teachers. You know how, what's the opposite of, addition? See, you know, right? It's like an undo operation, kind of, right? You add something, you subtract something. What's the opposite of multiplication? And what's multiplication? Well, that's like doing a lot of additions, right? Right? Like add 5 times. Oh, that's just multiplication. What's the opposite of multiplication? Division, right? Did you say subtract? Well, you subtract a lot. Yeah, it's like division, right? And then what does it mean if you mean if multiply is like add multiple times, what's multiply multiple times? Let's try that again. What's doing multiplication multiple times? Yeah, it's the exponents thing, right? And what's the opposite of exponents? Logs. It's the same thing, right? But for some reason, everyone's like, okay, that makes sense. That makes sense with the addition and multiplication exponents. And then okay, negative, and then division, and then log. Oh my gosh, log. No, it's the same thing. Don't let log scare you, okay? Anyways, log base 2 of this. It's like anyways, cool. But anyways, at the end of the day, there's no free lunch. The data's got to be sorted. I know, it's sad. Cool. Now, I've spoiled this surprise for a lot of you in here already. It came up in labs already, but we'll talk about it again. At this stage, everything we've seen has been in Python. But don't get it twisted. A linear search is a linear search whether or not it's implemented in Python or Java or any other programming language. The algorithm can be the same, but the syntax of the implementation of the algorithm can change. but it's the same algorithm. The algorithm and how you express the algorithm are different. In the same way that like I can have an idea and express it in English or in French, right? It's just how we express things, right? So the idea is the algorithm. And a lot of people start to feel uneasy by this stage. If you're in 162, you're like, man, we're changing programming languages. That's spooky. The algorithms aren't changing. The syntax is changing. And if you know the algorithm, all you have to do is ask Google, how do I do a for loop in Java? And you'll find the answer, right? The point is, you know you need a for loop. You know you need an if statement. That's what matters. So yeah, the underlying algorithms are the same regardless of the language. A linear search is a linear search. Even the syntax between the languages too. So even after all this, the syntax between the languages, like all these like really popular languages, so friggin' similar. It shouldn't spook you. So I'm willing to bet. Here's like a very general form of a linear search in Python. Linear search, haystack, let's say it's a list of integers, and a needle, it's an integer, and this is going to return a Boolean, right? So for I in range of the length of the haystack, so this will be 0 to whatever the length is minus 1, right? It's just a for loop. If haystack at I is the thing I'm looking for, I found it, otherwise, keep going. If I never find it, return false, right? Linear search, if the exam is coming up. If this scares you, make it not, okay? I can't give you any bigger hints than that. Here it is in Java. Your first reaction is, wow, that looks different, but look harder. It's the same. What does it start with? What's a function definition? This public, what's the, don't worry. Static, don't worry. It returns a Boolean, that's what that means. In the same way that means returns a Boolean. The name of the function is linear search. It takes an integer array, like a list, called haystack, and an integer needle. It's the same, okay? Then we have this for loop. Yeah, the for loop looks different, but for I starting at 0, well, I is less than the length of haystack, and every time we're going to increment I. I know we haven't seen plus plus before. Plus plus means plus equals 1. It's like a shorthand, okay? This is a for loop for 0 to the length of the collection. If haystack at I is needle, return true. If I ever finish, return false. Yeah, there's those braces, sure. But it's the same algorithm. Function definition, loop, condition, return. It's the same. Do you see what I mean? It's the same algorithm. You want to hear something wild? So that's Java versus Python. Python's actually the weirdest one in this group. It's the second weirdest one in this group. There's Java. Here's that same algorithm in C#. What's weird about this is it's actually identical. These are literally identical. The algorithm is exactly the same. Public static Boolean, linear search, an integer array of haystack called haystack, an integer needle, the for loop, haystack at I, yeah, return, perfect. Here it is in C++. Little bit different. What's this vector? It's basically a list, okay? For I, to the length less than the size, I++, haystack at I, return true, return, it's the same. It's exactly the same. Okay, with this haystack, it's the same algorithm. Do you see what I mean when I'm saying it's the same algorithm? Here it is in C. The biggest thing with C is like you can't, like lists don't know how big they are. Like arrays don't know how big they are, so you need to like tell it. So that's what the n is. That's just the length of that list. It's the same algorithm. Do you see what I mean? Historically, this came before the other ones, and this is actually kind of like set the standard for like this style of programming syntax. So C is like, you know. Do you see what I mean? So if you're thinking a new programming language, what I'm going to do? Don't worry.
It's just like Java.
Yeah. Now, here's an example of some syntax that looks weird. This, if I was switching to Haskell and people were like, man, I'm worried about the syntax changes, I'd be like, fair enough. Yeah, fair enough. Because yeah, that does look different. You want to hear something crazy though? That's like the same algorithm. I could argue that it's not quite the same. It's the same algorithm though. Because here's what this means. I'll very quickly tell you. So this is like the function definition. It's an equation on type A. It's going to take a list of type A where A is some arbitrary type. So think of like, if I were to say like A equals integer. Okay. So a list of integers and an integer, and it returns a Boolean. Kind of the same idea as before. And then here's what that first line says. So it's like positional. So it's like, okay, it requires a list of things and a thing. This line means, okay, if you ever see an empty list, and I don't give a shit what you're looking for, you're not finding it there. Imagine, for example, I'm holding a book in my hands. I don't need you to pretend I'm holding a book in my hand. I'm telling you, there's a book in my hand. Now you're all here looking at me going like, there's no book there. You're right. And if I were to give it to you and I say, find page 78 in this book, you're left going like, but there's no book. I can't find page 78. You're right. You can't. If I say, find your name in this stack of papers right here, and you're like, but there's no stack of papers right there. Oh, therefore it must not be in there, right? If I gave you an empty list and say, hey, can you find this thing in this list? You'd say, no. There's nothing there. That's what that line means. If you ever see an empty list and you're looking for, I don't care what, it's not there. Would you agree? The next line is saying, okay, break that list into two parts. The thing at the beginning and everything else. Imagine you have a list of length 10. This means like, okay, split it into the thing at index 0 followed by the things at index 1 through 9, right? So this is a single element. This is the remainder of the list. It's the head and the tail, they'll call it. And y. Y is some arbitrary thing I'm looking for. If x is equal to y, if the thing at the beginning of that list is the thing I'm looking for, this evaluates to true, we return true. It's done. If it evaluates to false, we go to this means or, by the way. Don't worry about it. Otherwise, do the linear search again, but only on the remaining part of the list. Do you see what I mean? Right? So if we initially looked at like A, B, C, D, E, F, G, it means do it again, but only look at the list B, C, D, E, F, G. And then do it again. Okay, it's the thing at the beginning of that list, the same. And if we ever get to the end, if I have the list of A, and I get the front of that list, it's A, and what's left in the list if I take A out of a list that only contains A? Nothing, right? There's nothing left. So if that's not A, we do it again. The last time it goes down to this. It's an empty list. It's not there. Long story short, it's the same algorithm, but yeah, the syntax is different. This would be fair. If you were to complain about syntax changing like this, I'd agree with you. But if you're worried about syntax changing from Python to Java, no. There's nothing to worry about. Don't worry. Any questions? All right. Was that a question? No. Cool. All right. I'll see a bunch of you in an hour.